Now let's talk about the energy contained in a capacitor. Okay. Energy in a capacitor. So what do we even mean by this? You see, you take a capacitor, it's uncharged, there's no charge on it right now. Now you are connecting it to a battery. Okay? And then the battery will charge the capacitor. Okay? So you will have positive charges on the one side and equal amount of negative charges on the other side. We're talking about parallel plate capacitors. Now, you see, to do this, the battery has to do work. Okay? The reason is, as we discussed before, initially when the battery puts the charge, there is no charge, no net charge on the capacitor, so it won't do any work. But the moment it has put the first charge on it, then when it puts another charge there, then it has to do work against this field, right? As we were talking about the potential energy of the system, what did we do? When you bring the first charge, you don't have to do any work. But then when you bring the second charge, then you have to do work against the first charge. And when you bring a third charge, then you have to do work against the first and the second charge. And when you bring the fourth charge, now you need to do work against the first, second and the third charge. Okay? So, suppose you go from charge 0 to a maximum value, Q charge. You certainly have to do work, right? So, because of this nature. So, what is the amount of work you need to do to charge the capacitor? And that is the potential energy of the capacitor. So, that charge is stored in the capacitor right now. So, you take the capacitor and connect it to something else, and the charge will start flowing. Now, you can use the energy that is stored in the capacitor. Okay. So, a typical example is your starter. If you have your scooty or a two-wheeler, you press a button to start it, right? So, actually it's a capacitor. A capacitor is charged, the charges are there. Now, when you press the button, you are closing the circuit. So, the amount of energy which is stored in the capacitor is now dissipated in the circuit. It goes and starts the vehicle. And once the vehicle is started, then your petrol will keep giving that energy. So, the rest of the things will happen. So, if you take a capacitor, you can store energy in it, and that energy can be used to drive something. Okay? In our case, it is the energy stored in the capacitor was used to start a scooty. Okay? So, energy is stored in the capacitor. And how do I calculate the amount of energy stored in a capacitor? That is what we are going to do now. Okay, so, this is the capacitor. Okay. So, initially it has no charge on it. And now I can probably connect it to a battery and then start charging it. Okay. Let me not use this wire right now. So, I am charging it right now. So, this capacitor has capacitance C. Okay. And then the capacitor also is going to be connected to a battery of potential difference, so that is V. Okay. So, you have C, V. So, C is the capacitance of this capacitor, and V is the potential you are going to connect across the two plates of the capacitor. And this will put a charge Q, right? So, this will put a charge Q. Finally. So, what is that? What is the relationship between all these three things? We know, right? C is equal to Q by V. So what have you done here? You went from 0 charge to a maximum of Q charge using this potential difference. Okay. I hope you follow the discussion. There is this capacitor, okay, uncharged, blank slate kind of a capacitor. Now you are connecting a battery across it. So the value of the potential difference is V. Now it is going to charge the capacitor. So the charge is going to rise from 0 to a maximum value Q. And the relationship between the capacitance, the voltage, and also the charge is given by this expression, C is equal to QV. So in that process, the battery has to do work, right? When it puts the first charge, it doesn't have to do any work. When it puts in the second charge, it has to do work against the existing charge. Then when it puts the third charge, it has to do work against the first and the second charges, and so on. Okay? So the charging takes it from 0 charge to a certain maximum value Q charge. Plus Q, and then you have minus Q here. Okay. So it is like this. It is like this. Initially, these were the two plates were neutral. So you take a positive charge here and then take it there. Okay? So then this will become negative and that will become positive. And again, you take another positive charge here. Take it from here and place it there. Again, this will become more negative and that will become more positive. So in that process, you will be doing work. Right? Okay. So that is what we will be doing. Finally, you have moved from 0 charge to Q charge. Okay. Let me take an intermediate case. Let us suppose that as it goes from 0 charge to Q charge in that process, okay, let's say like it has put Q amount of charges there. Okay? Let us suppose that you have put Q charges. You are not fully charged it. You started from 0, you keep putting charges, and I am taking one state where you now have small q amount of charge. Okay. The small q amount of charge. And you need to do work to put another bit of charge there. Correct? That is the work you will be doing. To take a small amount of charge and place it on this when there is already q amount of charge, small q amount of charge. Okay. You will do a small amount of work, right? Let's say, first of all, what is the amount of work? The small amount of work you will do when you take a small amount of charge from this plate and take and place it here. That depends on the voltage difference between them multiplied by the charge. Yes, what's the work done? Work done is equal to volt into charge, right? Volt into charge. If you remember, what is volt? Volt is amount of work done per unit charge. And if I'm going to bring q amount of charge, then the voltage potential difference into q will be the work done. Right? So, what would be the work done when there is already a q charge and I am going to take a small amount of charge, dq charge, and place it there? First of all, I need to know the potential difference when there is q amount of charge. How do I get that? Okay, I'll do it this way. When there is small q charge on the capacitor. So the potential difference across the plates would be what? The potential difference across the plates is going to be equal to, what would that be? E into T, right? E at that time. E when you have Q charge, E as a function of Q charge, and then D is the distance. But what is this EQ? The field. When there is Q amount of charge on this, small Q amount of charge on this. So how do we calculate that? So that would be, my E is going to be equal to, how much that would that be? E is going to be equal to sigma when there is Q charge. Okay, I'll do it this way. So it's small q by A by epsilon naught. So that's going to be q A epsilon naught. So that would be the E when there is Q charge there. Okay. So what is the potential? V is equal to Q A epsilon naught into D. Okay, so this you already know. This is also equal to see epsilon naught A by D is C. So this is equal to Q by the capacitance. This we know already. I hope you follow this. So what is the voltage V? I put this. What is the voltage V when there is Q charge on this plate? Then that is E when there is Q charge on this plate multiplied by the distance here. Okay. So what is E then? E is Q by A, that is sigma, by epsilon naught, and that is equal to Q by A epsilon naught. Then what is V? V is Q A epsilon naught into D, and it's actually equal to Q by C. See, remember what is C? C was equal to epsilon naught A by D. So that is the expression we used here, Q by C. It's a constant, right? A epsilon naught D are constant, so this won't change. So potential is now proportional to the charge. So the potential difference between the plates is now proportional to the charge. This expression also we knew, right? You see, CV is equal to Q. Okay. So at any and every point in time, if there are Q charges, small Q charges on it, then the potential across the plates of the capacitor is V is equal to Q by C. Okay. Now what is the work done? So work done, the small work, what I'm doing now, right now there is small q on this on the plates. Okay. Now I'll draw it here. And right now, let's say this is q. This is a q charge, not the entire capital Q, it's q charge. Now I'm going to take a small dq charge and I'm going to put it here. So this is my dq charge. I'm going to put it there from here. So this will become one more minus. So what's the work I'm going to do in taking this dq charge from here, plus here and then putting it there. So that would be d work done is equal to, what's the potential difference? The potential difference is V, and then what is that small charge I'm taking there? That is d q. That's the amount of work I'll do to take dq charge from one plate and put it on the other plate. So this is a small amount of work. What have I been doing? I have been doing this work where it was 0 till when it would be capital Q. Because I go from no charge to capital Q charge by charging this capacitor, by using this voltage. At the end I am going to have Q charge. In the beginning I am going to have 0 charge. But as I keep putting charges there, the voltage across this also is going to be increasing. When there is 0 charge, no voltage across the capacitor. But then you start putting charges, then the voltage across the capacitor keeps increasing. And you keep putting charges, and when will we stop? When the voltage across the capacitor is equal to the voltage across the battery. Then we will stop. Because these two are the same potential, these two are also the same potential, so no further flow of charges will take place. Okay? So the small amount is V, dW is equal to V into dQ. Now, what is the total work done? So this is the work done for taking dQ when there was Q. And once that is done, you will take another dQ and put it there, right? Now, because you have put one dQ, the voltage will have changed. Now you will do more work to take the next dQ. Now the voltage will again increase. Now you will take the next dQ and put it there. Then you will do even more work. Till when? Till this potential is equal to this potential. And at that time you will have a Q, capital Q, the maximum Q. Okay? So then you would have fully charged the capacitor. So if dW is equal to V dQ, then what's the total work done? So the total work done is equal to integral V dQ, and put it this way. V as a function of Q, V at Q, V as a function of Q into dQ. Okay? Function of Q, dQ. So what is V as a function of Q? This is it, right? So V as a function, let's put it this way. E as a function of Q is this, and then V as a function of Q is this. Hope it's clear to you. Initially I put E and V, but then if you look at E, E is a function of Q. If I take V, V also as a function, is a function of Q. So I'm going to take this. So now this is, and for how long will I be doing it? I'll start from 0 charge, and then I'll stop at Q charge. Right? So that's the integral we get. Now this is going to be equal to Q by C dQ. So V of Q is actually Q by C, and I'm going to have 0 to Q. So if I integrate it, then what I'm going to get? I'm going to get 1 by C into Q squared by 2, 0 and Q. So if you apply the upper limit, work done is equal to half 1 by 2C into, let's say, this is capital Q, right? So Q squared by 2C minus, I'll get 0. When I apply the lower limit, I'll get 0. So I'll stop with that actually. Q squared by 2C is what I get. So this is the work I will do. In this charge, this is the work the battery will do in charging this capacitor. Okay? So I want you to understand this. Initially, your capacitor is uncharged. Now you are connecting a battery across it. Now the battery will start charging the capacitor. Initially, the capacitor is not charged, so when it puts the first charge, the first dQ, there will be no work done. But when you put the next dQ, there will be some work done because there is already dQ present. You are bringing it in the presence of that field. Now when you bring the third charge, then more work will have to be done. Fourth charge, even more work will have to be done. So you will keep doing it, and then you will sum up all the work you have done. Till when? Till the charge goes from 0 to capital Q. Yeah. So that is given by this integral. So when you do that, you get W is equal to Q squared by 2C. Okay. I can write it in different ways here. Okay. Another way of writing it is this. What is this? Well, you see Q can be written as C into V, right? If Q can be written as C into V, see Q can be written as C into V from this. If you substitute that here, what do you get? W is equal to CV the whole square by 2C. So that is going to be equal to C squared V squared by 2C. So C squared V squared by 2C, and this will cancel. So what do you get? Now W is equal to half C V squared. Another expression. Same. This is the same as this. Now what else can you do? Well, I can say that Q by C. If we bring Q by C down and then take V there, Q by C is actually equal to V. So Q by C is actually equal to V. So if I put it here, then what would I get? W is equal to half Q squared and written like that. So Q by C can be written as V. So half C half, this is V, half VQ. Okay. So W can also be written as half VQ. So all the three equations are equivalent. They will give you the same result. Okay. The most important would be the second one. Okay. The reason being, what done is equal to half CV squared. It sounds like half mv squared, kinetic energy, right? Okay, it's not kinetic energy. This is again potential energy. But then it rhymes with that. Half CV squared, half mv squared, pretty much they sound similar. So it's easier for you to remember. But then there, in mechanics, the V means velocity. But here V means voltage, potential difference. N C is capacitance here and M would be mass there. So they're different things. But then it rhymes with that. So you can very easily remember this. What done? Potential energy stored in a capacitor is equal to half CV squared, which rhymes with kinetic energy in mechanics. Okay. So it will be very easy for you to remember all the three equations. I hope you understand this. Let me quickly summarize this again. You see, you have a capacitor, it's not charged yet, you are connecting a battery to it, then the battery will start sending charges, then the charge will go from 0 to a maximum Q and then it will stop. Okay. When it goes to maximum capital Q and it stops, this expression will hold good, right? Okay. C is equal to Q by V. V is equal to Q by C. V is equal to Q by C. So capacitance is fixed, voltage is fixed, then you know what the maximum charge on this will be. That is there. Now we are trying to calculate the potential energy stored in the capacitor. So now we are taking an intermediate stage, then we are trying to figure out what would be the work you need to do to take a small amount of charge from lower place, from this plate to the other plate. Okay. So when you do that, it's already charged to a certain charge Q, small q, is done, already done. Now when it is done, then it will have a field value here. And when you take dq, then you will do work against that field. Okay. So that field, when it has q, is this, and then that will have a potential VQQ, A, this is a potential there. And then the small work you need to do when you have this potential is VQ dq, so you get that. But then this small work will have to be done as you go from 0 to capital Q. You will keep doing it, right? You will keep adding charges. So every time you add a charge, you will do work. And all these small works will have to be combined to give you amount of work the battery has done in charging this capacitor. So that is given by this expression. So you got this here. Q squared by 2c is the expression you get. And then by manipulating this equation, you get the other two equations. And of the three, this is the most commonly used and most commonly remembered equation. Hope it's clear to you. Okay, the next topic is the energy density of a capacitor, or the energy stored per unit volume of a capacitor. Okay, I'll start with one of the equations that we have covered already. We said the energy stored in a capacitor is this. W is equal to half CV squared. So this is one of the equations, one of the three equations that we have just derived. So we take this expression and then let's try to do something here. Okay, so what is C? C is actually epsilon naught A by D. Okay, and then what is V? V can be written as E into D, the field inside the capacitor into the distance. Okay, that's work done, right? Per unit charge. So that's a potential difference between the two plates, E into D. If I start substituting these two values in this equation, let us see what we are going to get. So the work done or the energy stored in the capacitor is this. I have, instead of C, I'm going to write epsilon naught A by D, and then instead of V, I'm going to write E into D whole square. Okay, so this is going to give me half epsilon naught A by D into E square then D square. So the D and D can be cancelled. I can rearrange this equation this way. Write half epsilon naught E square to A into D. That's the work done or energy stored in a capacitor. So same as this, except that this is expressed in terms of the capacitance and the voltage across the capacitor, but here it is expressed in terms of the electric field inside the capacitor, multiplied by so the area and the distance of separation between the plates. And if you just think about it, I mean, I have this capacitor. Notice that it is level A and this is level D, the distance of separation. So it's actually talking about the volume contained, so within the two plates actually. So area and this distance D, right? So this is the volume we're talking about. So we can say that this energy, this total energy, is stored in that volume between the plates, the volume between the plates. Okay, and if this is the volume, notice it. So if we take to the other side, so we get work done by the volume. It's energy per volume, I'll say. Energy per volume or work done by AD volume. Okay, AD is equal to half epsilon naught E squared. So we call this quantity as U. U is equal to half epsilon naught E squared. So this is the energy density of the capacitor. Or energy stored per unit volume, or energy stored per unit volume. both are same. So what we've done is we've derived this expression W is equal to half CV squared, and instead of C we have put epsilon naught A divided by D, and instead of B we have put ED. Then when you manipulate these quantities here, then you end up with this expression, which is still the energy stored in the capacitor. But then this AD is like the volume contained within the two plates. So I can, if you bring them to the other side, then it is like energy per volume. So that gives you half epsilon naught E squared. So half epsilon naught E squared is the energy density of a capacitor, or energy stored per unit volume of the capacitor. So this is also an important idea. You will again come across it when you study electromagnetic waves. This is kind of a precursor to what you will be studying later. Okay? So remember this, energy density is half epsilon naught E squared. Okay? So energy contained in a capacitor can be written either like this or like this. In fact, there are three formulas like this, and there is one formula like this. So there are four formulas in which you can write the energy stored in a capacitor. Okay? Then we'll start doing an example problem and see if we can apply the knowledge that we've gained so far. Okay, let's do example 2.10. A 900 picofarad capacitor is charged by a 100 volt battery. How much electrostatic energy is stored by the capacitor? Now the capacitor is disconnected from the battery and connected to another 900 picofarad capacitor. What is electrostatic energy stored by the system? Okay. So a 900 picofarad capacitor is charged by a 100 volt battery. How much electrostatic energy is stored by the capacitor? The capacitor is disconnected from the battery and connected to another 900 picofarad capacitor. What is electrostatic energy stored by the system? Okay. Okay. So we have a capacitor. So the symbol for a capacitor is this. Symbol for a capacitor. Symbol for capacitor is this. This is a symbol you will be using in electric circuits. Okay, so this is the symbol. Kind of like you can see two plates, with a wire extending. So first is you have a capacitor here. So example 210. Okay. Okay. So this is 900 picofarad capacitor, which is connected to a 100 volt battery. So this is V and this is C, and V is equal to 100 volts. What is the energy stored? Clearly, you will have positive charges here and negative charges here. Okay. So you can see that, right? So negative charge will be repelled by negative 1 and then will accumulate here. Positive charge will be repelled by positive 1 and then they accumulate on the other side. So it's as simple as that. Kind of. So, you can look at it the other way. So you are connecting it to the positive terminal, so it will get positively charged, and you are connecting it to the negative terminal, it will get negatively charged. You can look at it either way. So what is the energy stored in this capacitor? That's easy. It's very simple, right? So energy stored in a capacitor is equal to half CV square. So half into, what is C? Is 900 picofarad. So 900 pico is 10 power minus 12. 10 power minus 12 farad. Half C, V is 100, so 100 square. Okay. So what I'm going to get now? So I'm going to get, there are 2 zeros here and there are 4 zeros here now, 6 and 10 power minus 12, so it will become 10 power minus 6, right? So I'll get 9 into 10 power minus 6 by 2 joules. That's equal to 4.5 into 10 power minus 6 joules. Okay. So this is the energy in this capacitor. So that's part A of the problem. And what is part B of the problem? Part B of the problem, you are disconnecting this. And then you are connecting another 900 picofarad capacitor here. So what will happen? What will be the energy stored in it? Okay. Let's see. Okay, so what is the voltage across this capacitor? The voltage across this capacitor will be 100 volts. So you can also calculate the charge, right? So it's very easy. So C is equal to Q by V. So you can calculate the charge V, and this Q is equal to C into V. So 900 into 10 power minus 12 into 100. Okay. So that is going to be equal to 9 into 10 power minus 8 farad, coulomb. Okay. So I can say it's 90 nanocoulomb or something. Okay. So we'll just leave it like that. Or you can say this 90 nanocoulomb. I can also calculate the charge there. Anyway, so you have the charge, you have this capacitance. So the voltage across the capacitor will be 100 volts right now. So what are we going to do now? You take this capacitor, which has 100 volts across. Then you have capacitance of 900 picofarad. And now you are going to, right now it has 100 volts across this. Okay? And you are going to take another capacitor, which also has the same thing. Capacitance of it is actually 900 picofarad. So you have plus here, minus here. Initially, the potential across this will be 0, right? It's not connected anywhere. Now you take this capacitor and connect one end to this, and then you connect another end to this. So what is going to happen now? So this is a higher potential, this is a lower potential. So charges will start flowing from there. Okay. Then this will get positively charged, this will get negatively charged. Okay. So then there will be charge sharing that will take place between the two capacitors. Okay. So you can think of it like this also. So you have a conductor here, you have another conductor. You are connecting these two conductors together, which means the charge will start flowing from one conductor to the other conductor. And when will it stop? When will the flow stop? When both of them will have the same potential. This must have the same potential as this one, and this plate must also have the same potential as this one. Then the flow of charges will stop. They will become one single conductor. Discussed that before, right? Okay. So till then, the charges will flow. Okay. Now, what is going to happen? What will be the potential there? Well, I'll do a general expression because it's going to be useful later also. So I'll do a general expression for this, and then we'll take that result and apply it to this specific case. Yeah. So watch this derivation closely. Okay. I'm not going to take 900 picofarad here. I'll just call this as C1, okay, and this as C2. So suppose that I have two different capacitances. So we'll approach it generally, then we'll come back to a specific case where C1 is equal to C2. Okay. So you have C1 and then you have C2. Now C1 has a potential V. Okay, or I will call this as now V1. Okay. And now what are we going to do? I am taking C2 and connecting it across this capacitor. Charges will start flowing, and when will they stop? When as charge is flowing, then voltage will be built up here, and when this voltage is the same as this voltage, then the charge flow will stop. So that is when they will stop. They become one single conductor. The potential across the conductor will be the same. So then the charge flow will stop. So we are going to have, let's say, V2 here. But the condition, the electrostatic condition is this. When V1 is equal to V2, then it will stop. So you start with V1, or let's say you start with V. You start with V, you start with V. C1 versus V. And what happens finally? C1 will have V1 and C2 will have V2, but V1 and V2 must be the same, then it will stop. Okay? I am starting with V. Now, what would I have? The electrostatic condition V1 will be equal to V2. Yeah. So, what's the voltage at which it starts? Well, what is V1? V1 is actually, from here, V is equal to Q by C1, right? So, I will say that it is going to be Q1 by C1. Why? You started with Q charge, now you got Q1 charge here. So, you are going to share it, right? Share the charge. So, Q1 by C1 must be equal to Q2 by C2 in the final state. Okay. But what else do you know? The conservation of charge. Q1 plus Q2 must be equal to Q. Right? Okay. So what do we get here? Q1 plus Q2 must be equal to Q. So Q1 must be equal to Q minus Q2. So let's keep it there. Initially, when you had V voltage across C1, it had Q charge, and the capacitor, you could have written like this, right? The capacitance could have been written as Q by V initial. That was initial condition. And this was 0. It's not zero. Now you have started you connected them, things have started flowing, then you got here. So can I do this here? Okay. So Q1 I'm going to have Q minus Q2 by C1, and that is also equal to Q2 by C2. So let's do things the regular way. So I take C2 there, C1 there, and get C2 into Q minus C2 to Q2 is equal to Q2 into C1. So if I bring Q2 there, C2Q is equal to what? Q2 into C1 plus C2. Okay. So what does it give me? So Q2 and written as Q by C2. I'm sorry, Q by Q into C2 by C1 plus C2. So Q2 can written as C2 into Q by C1 plus C2. And if we do the same thing for Q1, we take Q2 and substitute that there, you can see by symmetry Q1 will be equal to, I'll draw it here. Q1 can be written as Q into C1 by C1 plus C2. So it should have. Like that? Okay. So you got, you know like how Q1 and Q2 will split across the capacitors. Okay. So what would be the voltage across these? C1 into V1 will give me Q1, but V1 will be Q1 by C1, right? So voltage across this one, V1 is equal to Q1 by C1, so that is going to be equal to what I can say, Q, okay, this is equal to QC1 by C1 into C1 plus C2, right? So this is Q1, this will cancel, so I will get capital Q by C1 plus C2. So that will be the voltage we have. Okay? Okay. So, but what is Q? What is capital Q? The beginning. That was equal to C1 into V, right? So I can do it here. So V1 is equal, instead of Q, I want to say C1 into V. That was the original thing, right? By C1 plus C2. So that is going to be equal to V into C1 plus C1 plus C2. Okay? So this would be the voltage shift. So this is a very important expression. See, finally V1 will be equal to V2, right? So V1 will be, so V1 final voltage will be like this. V1, which is going to be equal to V2 finally, and it must be equal to V into C1 by C1 plus C2. So very important expression. So remember this. So what have we done here? So we've taken a capacitor which was charged to voltage V, the capacitor value is C1, and I am connecting another capacitor C2 across this. The charges will flow and then they will reach an equilibrium where this voltage will be equal to this voltage. When this voltage is equal to this voltage, what would be the relationship between this voltage, the final voltage, to the initial voltage with which we started, which was V, right? So V1 is equal to V2 is equal to V into C1 plus C1 divided by C1 plus C2. Okay. Assuming that C2 is also equal to C1, then what happens? C1 by 2 C1. So C1 and C1 will cancel, we will have V by 2. Okay, so that is what we have here. So what did we, in our problem, what do you have? C1 is actually equal to 900 picofarad and C2 is also equal to 900 picofarad. Since both of them are equal, so it's going to be C1 by 2 C1, C1 plus C2, 900 plus 900. So you will get V by 2 as a final voltage. Okay, so V by 2 will be the final voltage. So V in our case, okay, I'll do this. In our case, the problem that we have taken on hand, It's like this. Okay, V1. So V1 is equal to V2 is equal to V by 2, because C1 by 2 C1 same thing. So V by 2. So that is equal to 100 by 250 volts. Okay. So you will have 50 volts here. You started with 100 volts. This was with 0. So you connected this across this one. So because these capacitances are equal, then the final voltage will be half the voltage you started with. Okay. But if it is not equal, then that is not going to be the case. You see, then this will change. Okay. Suppose it is 900 and suppose it is 100. So what would you get here? So 900 divided by 1000. So 0.9 into V. So 90 volts will get. If this is just 100 picofarad. Okay. So keep that in mind. Because these two are equal, the final voltage is actually half of the original voltage. But this is the expression. Final V is equal to original V into C1 by C1 plus C2. Okay, let's come back to our problem. So this is 900 picofarad, so the voltage will be 50, voltage will be 50 here. Perfect. Okay, now what's energy in this? What's energy in capacitor 1? Capacitor 1 energy is equal to half C1 V1 square. So that is again half into 900 into 50 picofarad, right? 9 into 10 power minus 12 into V is 50 square. Okay. So, or I can say this is 100 by 2 square. Either is fine. Okay. So, okay, then W2 is equal to half into C1, which is energy in this capacitor. After you stored it, after the discharge is taking place. That is equal to half into, because C1 is C2 V2 square. C2 is also 900 into 10 power minus 12. Then V2 is also 50, I'll say 100 by 2 the whole square. Okay. So then what's total energy? Must be equal to W1 plus W2. So I'll add these two. Okay. First, what's the value I'll get here? So this, you remember, was the energy you had in this first. So what was that? That was equal to 4.5 into 10 power minus 6 joules. Now 2 square will be 4. 1/4 of it. What's the energy here? Same stuff. This already done that, right? So this was equal to same 4.5 into 10 power minus 6 joules by and 2 square 4. Okay? So when I add these two, then what do you get here? I get 4.5 to 10 power minus 6 joules by 2 actually. That's the energy. So this must surprise you. You started with 4.5 10 power minus 6 joules here, and then you connected another capacitor here. So the energy was shared with this capacitor. So then if you add this energy and this energy, then they must be equal to the original energy, right? I should have got 4.5 10 power minus 6 by adding energy in this and energy in this. But when I add this energy and this energy, I am getting only half of the original energy in this case. So what happened to the remaining half is a question. The remaining half was lost in radiation and in heat. When the charge was flowing through this, then there was this heat and radiation loss that took place. And it's because accelerated charges will radiate energy, which is something that you will come across in your electromagnetic waves lesson. But this anomaly, this mismatch in the total energy is caused by radiation losses. When the current started flowing, part of the original energy was lost. Okay? And that is why this energy and this energy together do not match with the original energy. There is a certain amount of energy which has been lost. And that's half of, in this case, half of the energy has been lost in radiation. Okay? If you start with 100 units of energy with one capacitor, you connect another capacitor, energy is shared between these two capacitors. So when you add this energy and that energy in the final state, you would expect the same 100 units of energy to be present. No. What you have in this case is only 50 units of energy in both together. I mean, one has only 25 units, and the other also has 25 units of energy. So if you add these two things together, then you get only 50 units of energy. You started with 100 units of energy. So 50 units is missing. What happened to it? We conclude that it was lost as radiation. Okay, because accelerated charges will radiate energy, and because the charges went from here to here, in that process, radiation losses took place. So they went out as heat. Okay, so that is the inference we make. Think about it, and even if you don't understand the final point of radiation losses, just keep in mind that they have been lost due to radiation. Okay. And you will understand it. You will understand why it was lost when you do the electromagnetic waves lesson. Okay. So till then, you understand that you have a capacitor, you charge it, you store a certain amount of energy, and then you connect another capacitor to it. A part of the energy is lost in radiation. Okay. So the sum of the energy in both the capacitors finally would not be equal to the original energy you started with. Okay. Hope it's clear to you.